All right, everyone, welcome to MLC Research Jam number 27. We have a few talks this time that were already done, not recorded, and a few talks that will be recorded. We have these research jams every couple months where anyone can call in from anywhere in the world and present what they're working on, whether that's ideas, had an idea and I haven't started work at all, but I'd like collaborators, or it could be I made some plots, or it could be a whole research project in progress and kind of seeing recurring updates from those. First up, we have Kira Intratour. Kira, do you want to share screen and take it away?
Sure. Thanks so much. Let me know if you guys can see that.
Yep, we can see it. It's not in presentation mode. Now it is. Great.
Okay, fantastic. Thanks so much, Jason, and thank you guys. So just a quick background before we dive in. I work in international development, and so I look at messy development problems and how to leverage AI to make the solutions more simple. I'm also an urban planner by training, so I meld the two for this. So this is going to be more of a discussion on what the problem was and the solution and product that we created as a team. So for context, this was deployed, the GeoAI tool, or Geographic Information Systems tool, was deployed in India, Syria, Afghanistan, Pakistan, and Kyrgyzstan and Tajikistan. I think maybe I said those twice. So what did we have in the organization? We had some really good field data. We had really good GIS experts in the field across these countries. What we didn't have was urban planners, and we didn't have a decision-making system to look at disaster mitigation, disaster risk from a spatial perspective. We didn't have ways to inform local government or organizations for investing in critical infrastructure, whether that's roads, hospitals, access points, the basic information an urban planner might need, right? So how do we create a method and a model that can be scaled across very diverse cultures and countries? And most of them, except for India, have a huge lack of data in the regions that we were addressing. So what do you do? So the first was, how do I create a methodology that can be easily accessible to non-urban planners across this NGO? And so created a kind of a linear system. There's a lot of research behind this, but this is the most simple visual I wanted to show around the different steps of urban planning. They're interchangeable, there's like data behind it, milestones. And I wanted to just focus on the fourth step, which is the data analysis for land use planning. And this is where we use GeoAI.
Kira, can I ask, to make this more concrete, can I ask for just a single example of what type of project and planning are we talking about in this cycle, and how might you help?
Sure. So it could be, the government in Pakistan wants to build a new hospital, but they don't know
Mm.
where to do that. Uh,
Okay.
they don't know the demographic forecasts. They don't necessarily know who's being served and how. What is the infrastructure there? How are the transit access points? What is the future forecasting of either demographic use or change over time in terms of the way people using their land or access to services? So some of the
Mm.
key questions this can respond to is, what are the critical services that you have? Or
Mm.
as a government, where are you going to invest in these services in the built environment? Because once you build, you can't it's harder to unbuild, and there's a lot of money going into it, so you better make the right decisions. Or to attract foreign investors. Or you could also answer, okay, there's flooding or glacial melts due to climate change. Where are these? Or what are you going to plant, right? what soil typologies do you have? So whenever you have different geographic information systems data, you can ask these types of questions based on the layers you have. Does that respond? Does that answer?
Yeah, I think I get it. So the holy grail here is some super smart Uber Google Maps that contains lots of layers with all the relevant data and somehow can also, aggregate them and predict the future. Like, what is this going to look like later? Maybe, maybe. If we had that system, a lot of these tasks would become more easy.
Exactly. And so the way we structured this is I looked at a lot of data sets in municipal planning from different countries, right? What are the different data layers they have? So obviously it's demographic, socioeconomic, information, basic services and infrastructure, environmental analysis like topography, soil typologies, housing parcels, right? Like what is, not just the housing parcels, but like how tall are they? What's the density? Who's, how many people are living in it? So, and the building stock, you know. So this is your kind of typical, I would say, generic data layers. And so a lot of research went into this. Like I wanted to understand what countries had what data, how, and obviously they have different legends and information. So that was the starting point. Like the problem, how the data was structured, and then we had different types of data sets with every data layer. So this is like services and infrastructure, public transit, like where do they go, what's the coverage, what's the frequency. All these things are very, I would say, commonplace for a city or a municipality hopefully to have at their fingertips, but we don't have this in the developing context, and we should, right?
Mhm.
Why
Cool. That
not?
makes sense. Yeah.
And then here we were using satellite imagery. Obviously, there's different quality, but what we wanted to do is have standards set across our regions for the data source and the standard of the resolution. So we also did some standard setting here. We also used OpenStreetMap data for this, and supplemented where needed, right? Because again, there's a dearth of information, but we also want to ensure that there's equality there. Data sources like NASA, there's Sentinel data, USGS has really good information, Aqualand, and then we also did different Esri models. Already has a lot of GeoAI built in, a lot of really good analysis there. So we just pulled from this and then created a model out of it. And so the AI portion of it was around modeling, right? So we did this for climate change modeling. So one example is with climate change, we have heat islands, which is where, you could think of like in downtown Mumbai, you can have a heat island and it's trapped, especially because of all the cement. But that same heat island in a coastal region is going to be defined in a different way versus in the mountains in Gilgit in northern Pakistan. So we had to also adapt, how we were defining heat islands in each of the regions that we were analyzing, but at the same time, you could still have the same algorithm behind it. So we, the great team also made sure that there was different elements, then looking at flooding and snowfall, and then we did the NTVI, the slopes and elevations and terrains against that to use that for our particular cases. We're also looking at change over time, growth, which is really important. Like even in a rural setting, how is someone using their house? Are they adding to it incrementally? Who's living there? Are they using agricultural land in a different way? Because that will inform who's coming in and out. What are the migration patterns? Um, and so we were looking at that and climate monitoring as well. And then for some of them, we either pulled from Esri or had our own coding in Python. There's also some really great GeoAI science libraries that are readily available, but in all cases, we vetted the quality of the information, whether that was road, data aggregates because we might have missed one in 1 year. So we used AI to kind of fill in the gaps there on the geographic information systems or temperature data, again, for the climate modeling, while keeping the nuances between the countries and regions that I had mentioned. So in each of our countries, we had different expertise. So we made sure to leverage those. So we had great geologists in one country, or, different climatologists or flood modeling in another. So we would build off of that knowledge. So with rockfall modeling, we had it in one country. Flood and gloff melts in Tajikistan is extremely strong with our scientists there, because Tajikistan has the Pamir Mountains and has a very unique topography of mountains as well. So, and the research that they do locally. And then digital elevation models are quite common. So we use the Esri Python library for that. I think what's really hard in I guess with any project in the development sector, but obviously there were tons of nuances based on data availability, is demographic information, or just like holes in your data. So that's something that we still need to go and, either do surveys or do ministerial connections in terms of government analysis. But even there, you have to question some of the information. When was it collected? How? So those statistics are very important, but so we need proxies as well for those. So here's an example of one of the projects we did. This is in the Kyrgyz Republic. We did this with the UN. And here it's an example of what you were saying, Jason, like, what does it give you when you overlay? So this, for example, we can see insufficient mobility infrastructure. So what does that mean? Or what are the green spaces? Or where are areas of high risk? And so we're not telling exactly what the government should do or what the decision makers should do, but we're giving them really strong data visualizations to then analyze it and giving the tools to them. So I would say with AI and international development or global impact, you also have to make sure that the tools are scalable and usable by an entity that will continue using them in the future. And so in Central Asia, what we found is we encouraged some of the governments to use it as a finance tool as well, like capital investment planning. You can use it for that. You can use it to attract foreign aid investment in critical infrastructure, whether that's in energy, with hydropower, etc. So you can use these tools in different ways, and incentivizing your end user to also utilize them is important. So here in Khorog, we also did stuff in Tajikistan, in hazard regions, etc. So I don't know if I'm at time.
A couple minutes left for questions, if yeah.
But I think I started with you asked that question, but this tool can be used for a myriad of things. So yeah. And if you guys want to connect with me, learn more, I just put my LinkedIn there. Thanks.
Can I ask, what are you looking for? Collaborators, people to use the tool?
I'm not sure right now about this tool. I think in general, I want to reach out to people who are at the intersection of AI for social good or AI for impact, because what I'm seeing is that there's a lot of talk. Where does the rubber hit the road, right? So we scaled this across like 6 countries, and it's being utilized by major government ministries. So I would love to learn from the community, what else can you think of in your own research that could then help with, I know it's a very large question, but with global health or education or those things, right? Who do you see is leading the charge here? How can you incentivize organizations to actually do AI for good if it doesn't have that return on investment? And if it does have a return on investment, what does that look like? So I think for me, it's more of a philosophical question rather than a, hey, use this product necessarily.
Hmm.
Thanks, guys.
I think Lass has a question.
Yeah, hello. So I'm gonna say this at the risk of sounding quite naive. I'm not a very experienced researcher, but I didn't really understand the technical parts of this project that you have. For example, you mentioned the representation of, was it like heat zones or something like that, or you mentioned the models, but I wasn't sure what kind of techniques you were using and that sort of stuff. I would love some clarification on that.
Yeah, and I'm happy to go also offline in terms of what they are. Each of them has a different algorithm, right? So for urban heat islands, there is different, what's the density, what's the material, what is the recording of temperature over time, et cetera. And so that will apply different algorithms for each of the questions that we're asking. Or it can be more static. So for example, say you just want to know access to um, a hospital, then you'll take the distance of a neighborhood to the nearest hospital, and you'll look at different access points. So it's more simple and straightforward, and that's more of a two data layers in GIS overlaying, and you querying that visually. So it depends on what it is. Like the more complicated ones, I would say, are gloff melt or glacial melts or flooding, right? Because there's prediction around that for climate change. Rock falls have their own algorithms as well. So it depends. Or access to civic amenities is a more direct one, because you could say, okay, the walkability of this area is like a 15-minute walk, or you can say this is a road that's paved, so it will take X amount of time on this form of transportation.
If people want to get in touch, is your LinkedIn here the best way?
Sure.
Awesome. Well, let's thank Kira. Thanks for presenting, Kira.
Thank you.
Up, next up we have Attarva Bhutani presenting. Attarva, when you're ready, you want to screen share and take it away?
Yep, just a second. So is my screen visible?
Yep, looks great.
All right. So hello everyone. I am Atharva Bhutani, a 16-year-old high schooler who decided that building an LLM in my bedroom would be fun. So just a heads up, this is going to be a very high level idea because I don't have formal ML education because of course I'm in high school. I don't have enough math experience to comment on anything. So this is going to be a high level idea, barely anything technical. Right. So I'm just here for the vibes, for reading some research papers and collaborating with people and building something worthwhile. All right. So this project is about making an LLM that does not try to understand everything. It just knows when to pass the mic to someone smarter. Let's say one analogy to understand it is that you don't ask your chef to fix your hard drive. So why rely on one model to do everything? And the core idea is let the math guy do the math stuff, let the coder handle the code, and so on. It's like a group project, except the smart kids don't get stuck with all the work. All right. So the LLMs that are currently available on the market, they give all of their answers from a single pool of knowledge. But what if we have several experts who specialize in one field of knowledge and then we make them answer our questions accordingly? So we might say that we have models like that, and they're called multimodal or MOE, mixture of experts. But the current mixture of experts only focus on type of input. Like the current ones that are readily available, they focus on type of input. Like some focus on video input, experts focus on video inputs, one expert focuses on text input, etc. But they derive all of their answers from a single pool of knowledge, from a single pool of training data. But if we have different experts, they are trained on different types of different domains of data, right? So let's say one expert is trained on physics data, while one model is trained on code data. So we can create efficient mechanisms that take our input and they activate those experts accordingly, Right. And one more problem with current MOEs is that they are really hungry for computational power. So what if we build something that solves both of these problems? A lightweight domain specialized MOE. Right. So this is going to be the basic structure for the expert, basic decoder only transformer model, which is built from scratch, right? No PyTorch or no TensorFlow. I built this with just me, NumPy, and some tiers. I defined the weights with Hay and Xavier initializations and also the biases. The forward passes are all manual, right? So I learned the coding or learned ML from coding this project itself because I didn't believe that learning theory would be that important. I thought that diving into the deep end would be more worthwhile. All right. So after building an expert, here's how I plan on transitioning to an MOE. The main question in my mind right now is how do we use our input to figure out what kind of question it is? Do we build a classifier that classifies based on tags? Do we find cosine similarity between the input and expert vectors? This question is what I need answers for. And currently for me, I find that the best option is classifying data based on tags. We tag data based on domain, and then we train one expert tag with physics, one expert tag with code, etc. And then we make a classifier that predicts the domain of our input. So this is the theoretical architecture. So our MLPs are going to share an attention stack, but then that routes into the domain classifier, which figures out what domain of input it is, and then it routes to its own MLP and gives us the output. So this solves the two problems that I discussed earlier. That if we only activate a number of neurons per input, right? So it does not need to activate the whole model, and the compute power is decreased exponentially, and the speed increases also. So this can also result in increased scalability, because if we add more experts, that isn't going to change how many neurons are activated per input. So we can scale comfortably without reducing the speed or anything. So all of this might sound like sunshine and rainbows because I am presenting these ideas very happily, but I know that a lot of challenges will also be faced because what if it predicts the wrong domain? Or how do I figure out how much of each domain is to be used? Or how do I keep the model balanced, etc. But I believe that with this ML collective and with the help of like-minded people, I can get through these challenges and build something worthwhile. So what's next? My plan is to finish building the transformer, create a classification mechanism, and then train my models on different areas of knowledge and see where it takes me. There are also a number of things I'd like to play with. Like instead of a regular transformer-based application, I want to make a diffusion-based LLM and see how that competes to current LLMs and train on real-world domain data. And I want to use different training techniques, maybe use LCA as you proposed for training. Right. So that's it. And here are some papers that inspired me a lot. I don't completely understand all of them, but these really inspire me to work towards something more. And yeah, that's it. I know this was pretty short because it was a pretty high level explanation. Thank you for listening to me rambling about my passion project. I'm looking forward to being a part of ML Collective and collaborating with like-minded people. So you can connect with me on Twitter, GitHub, or through email. If you have any questions, feel free. I'm open.
Thanks for presenting, Attarva. Maybe I should have asked some questions during the presentation. Can you put the slides back up?
All right, just a second.
Certainly it's super
Yeah.
super impressive that you're starting this so soon in high school and everything. Um, Maybe I missed it, but let's say you have five experts available to you, and you don't know ahead of time which one is going to be best for a given segment of generation. What's your sort of ground truth for which expert should be selected?
So yeah, that was the main problem that I highlighted. That this is what we need to figure out. Right.
Mm.
So I mean, tagging based on domains is fine and all, but what if it gets confused, right? So that is the main problem that I'm experiencing right now, and that is what I basically need help on. So any
Mm.
suggestions that you might give me, or in the Research Jam channel itself, or any platform that you can connect with me on, I'd be willing to discuss anything that you have in mind.
So one idea, and I don't know whether 10 papers have already tried this. But one idea is you could take a big set of data, a big corpus containing many topics, feed it through all, let's say, 5 language models. For each language model, get a distribution for what the perplexity looks like, so what the loss looks like over that example. So model 1, it's a little histogram. This is the typical distribution. Model 2, here's the distribution. Maybe model 2 is better at almost everything. Model 3, model 4. Then for a specific example, look at either, which model models it best, so which model understands that domain best, or maybe look at which model has um, the perplexity, like as a percentile of its own perplexity, the lowest. So like maybe one model, so maybe all 5 models are approximately equally capable, in which case the distributions would be roughly the same on average, but some models are going to have really low perplexity here and others are going to have really high perplexity. Then you could learn to route to the models that are predicted by your model to have low perplexity. In another world, there's going to be 4 dumb models and one model that's simply better at everything because it's the biggest. And then I guess you got to figure out what to do. Maybe use the percentile idea, or you have to figure out how to balance always calling a good, smart, expensive model and routing to a model that's much cheaper, but it's going to be a worse answer, maybe. But I don't know.
Yeah,
Anyone else have any thoughts?
that's a great idea. No, that's a great idea. That was basically what I was thinking, but
Hmm.
it was pretty theoretical. I need to get into theory a little bit to understand these better. So yeah, that's it. Thanks a lot.
Okay. Any other folks have thoughts for Attarva or questions? Feedback? One more
I
question.
I think yeah, I was just wondering about the fact that like if you train one model on only one domain, the fact is like different domains, like the research ideas usually come from, like, you try to mix different domains to come up with the latest research ideas. So I mean, it might not be good in that perspective.
No, I get your point.
Uh,
I
yeah.
believe I said that in the pitch. I don't think I did, but
Uh,
the classifier is not just going to take the answer from one model. It is going to take the input and is going to merge answers from, let's say, one input activates 2 models. Like I have a question which goes into the field of physics and code as well. So it's going to
okay.
activate the physics expert and the code expert, and they both are going to give an answer which is going to be suitable for it. I don't think
Okay, cool.
it's a right. Yeah.
Cool. Any other thoughts or questions?
So I believe in the chat somebody wrote that at the end of the day, the training data is the same. So that was the main point, that the training data is in most cases not the same. Um, I am going to train different models on different data itself. That's how it is going to become an expert in that field. If I train all the models on the same kind of data, they are going to have some specialization in some field, but not exponential. So training on different amounts of data is the main point of this whole MOE.
Makes sense. Makes sense. Yeah. All right. Well, thanks to Tarva for presenting. It was awesome. Great ideas and directions, and even more impressive than average due to you being in high school. Crazy. Great. Our last presenter is Hari Prakash, presenting work with Charles Martin. Both of them are on the call. Hari, do you want to share screen and take it away when you're ready?
Sure. Yeah, just let me know if the screen's visible.
Yep, we can see
Okay.
the whole browser.
Yeah.
Yeah.
So the idea or the thing we wanted to present today was grokking and generalization collapse from the perspective of HTSR theory. Going into the specifics of what is grokking. Grokking is this phenomenon where you have this delayed generalization, where you train and then your train accuracy hits almost 100%, and then your test accuracy has a huge increase a bit later. We were inspired by actually studying this when we were looking at a couple of progress measures from Anthropic, DeepMind, so on and so forth, where we wanted to understand what is actually happening in terms of memorization, in terms of generalization, because there have been quite a few papers that talk about a phase of memorization or a phase of generalization. So we wanted to understand, are there more phases that exist, or what exactly is going on? So one of the things that we did was take the Grokking puzzle, which generally runs up to like a million steps at max in traditional literature, and extend that to almost 10 million steps. So you have this experiment run over days, basically. And we found something very interesting. We found that after a million steps, we see a decline in the test accuracy. So we had this question of what exactly is going on. Is it overfitting? Is it getting confused? Is it memorizing? Like, what precisely is going on? So that brings me to the next slide, which is taking some of the existing progress measures and applying it on this exact scale of 10 million steps. And what we see is, of course, the weight norm, which was theorized to have some explanation on regularizing the entire network, didn't quite do the same thing over here. If you notice, and also I forgot to mention, that the weight decay here is set to 0. So you're not explicitly regularizing this entire model. You're saying, I'm having absolutely no weight decay. I'm just running the whole thing with 0 weight decay. So you would expect kind of like an increase or a non-decreasing weight norm, which is what you kind of see. So we can definitely say that a decreasing weight norm isn't exactly the cause for this move from memorization to generalization and so on and so forth. We also importantly don't see within the weight norm, for example, the fact that you have this huge test collapse. It just keeps going up, essentially. It goes up from 10 power 5, 10 power 6, and then you have a huge explosion from 10 power 6 to 10 power 7. The other progress measure, which is activation sparsity, and this one is interesting because it shows some sign that there is something going on in terms of the dip. So you can see the inflection point at around 10 power 6. And if you just move back up here, you see that at 10 power 6, you have your max, approximately at 10 power 6, you have your max test accuracy, and then that dips. So you do see that the inflection tells you that something is going on, but doesn't quite show you that there is such a huge dip in the test accuracy. And this is something interesting that we'll come to in the other weight decay experiments, where you still see that dip within activation sparsity, but in the weight decay 0.01 experiments, you see the test accuracy is flat. So it basically kind of fails the negative control.
Hari, can I ask a question here?
Sure, yeah.
What exactly do you mean by activation sparsity? And I guess, how are you computing it?
Right. So I can pull up the detailed paper.
Don't do that.
Oh, yeah.
There are a couple of progress metrics for measuring grokking. Activation sparsity is from Google, right?
Yeah. So
Right.
yeah.
And do you have it? You don't have it in the deck?
No, I didn't put the definition, but essentially what you're trying to look at is what percentage of the neurons are below a particular activation threshold.
Is the activation threshold 0? Or like, are they literally exactly 0 or not? Or is like
no. So your threshold, I think you can preset this. So this paper is by, I think, Satvik Golecha from ICML, I believe. And he shows that you can pick a particular threshold and then measure what fraction of the neurons are below or above that threshold in terms of activation. So for example, let's say that value is like 0.3 or something. You're measuring within the neural network, which by the way, over here is a 3-layer MLP. You're trying to look at within this neural network, how many of these neurons have activations above that threshold and below that threshold. So
is that threshold chosen once upfront for the whole training run, or does it float at all?
Sorry, say that again.
Is that threshold chosen once upfront for the entire training run?
I believe so, yes.
So if that's the case, then are you really getting to above 99% sparsity here, as in almost everything is below the threshold?
Yeah, so that's what it would seem like, which is essentially as I progress through training, the sparsity or the number of neurons below that particular threshold is almost 100%.
So what I would ask here is it the case that all the neurons that are below that threshold, but still a little bit above zero, is it the case that they're all useless and not used? As in, if you set them all to zero, would you get the same answer? Which is a
Right.
strong conclusion. Or is actually all the representational power in that whole set of neurons that we're calling not firing above a
Exactly.
threshold? And the
Yeah.
entire story is there, and we're just measuring this, which is not really then kind of sparsity.
Right, yeah, which is why we kind of augment it with these other measures, which is the HTSR measures and also the other measures that they propose, which is local circuit complexity, which
So
asks this question on how many of these neurons are useful, how many of these neurons are useless. And basically with the circuit complexity, what you're doing is you're taking your MLP and then you do a dropout, you shut off certain neurons and you look at the final logit distribution. And then you do dropout and then see how that distribution changes. And you take the KL divergence between the two, and that's what local circuit complexity is. So to your question of how would I figure out which one is useful and which one is useless, you would expect that after dropout, if I still have the same logit distribution, then nothing much has changed. And what I learned is kind of distributed, basically. But the most important point here is that the progress measures that were proposed don't quite differentiate that first start point from the anti-Grokking phase. Yeah.
Because that's really the key thing.
Yeah.
Right. You train the model to interpolation. There are different metrics that detect Grokking, but there are two different phases of interpolation, and you can't detect which phase you're in. So the interpolation is not just interpolation, there's something else going on. So that's
Exactly.
I think what you're
Yeah.
trying to say.
Yeah. Long story short, basically you're trying to take these progress measures and you see that they don't quite explain the difference between pre-Grokking and anti-Grokking, which is this portion as compared to the last portion. So now what you're trying to do is use HTSR to figure out, hey, what exactly is going on? And before I get into the definition of HTSR, it's nice to kind of internalize these plots, which is you have this threshold that you set, which is a theoretically defined threshold in HTSR theory for the optimal state for a layer, which is alpha equal to 2. And you have certain conclusions based on that. But what you do see with HTSR theory is that you see a differentiation between pre-Grokking and then Grokking and then anti-Grokking. So
what's alpha here? Can you just define what you mean?
yeah. So I'll come down to exactly what we are doing in terms of alpha. Just one moment. Yeah. So we take each layer and then we are basically taking a look at the correlation matrix of the layer. And then we visualize the empirical spectral density. So we're just looking at the eigenvalues. And HTSR theory basically tells you that if you see a tail or this heavy tail behavior and you can fit it to a power law, then you see that it is in a certain state
Go down a
of
slide.
learning. Yeah. So for example, you fit, let me just one moment, it's kind of lagging. Yeah. So this is what you're doing. You're taking your ESD and then you're trying to fit it to a power law tail. And the alpha here is basically the exponent for that. So when we say alpha equal to 2, that means that your power law exponent is 2. And theoretically, HTSR shows that if I have an alpha equal to 2, that my layer is in its optimal state of convergence. And the idea is that when I deviate away from 2, suppose I'm really big, like as you can see over here, 5 to 6, it's almost random. And that kind of feeds into some of the stuff on random matrix theory with Marchenko-Pasteur distribution, so on and so forth. So you would expect that when I initialize the model, I would have a huge alpha because it's extremely random. I would not expect to see any correlations or heavy tail. It would just follow Marchenko-Pasteur. And then as I keep training, I come down to the optimal alpha, which tells me that my model's layers have learned something about the correlation in the true data. And alpha equal to 2 is the point where it performs the best. And it's been empirically shown in, I think, the previous HTSR paper, and theoretically shown that this alpha equal to 2 is kind of its optimal state. Now, the interesting thing is when I keep training and alpha falls below 2, this is what indicates that you have over-correlation, or these things called correlation traps. So just
This is the anti-Grok.
Yeah. So
go back up and show the plots.
Yeah. One moment. Yeah. So, oops, and it's going up.
Yeah, I think we saw at the end of the plots, the alpha dips below 2.
Yes, exactly.
Conclusion.
So you see, and what's interesting here is you can see this layer-wise, because you're basically taking the weight matrices for each layer, is that I can see that FC1 has a slightly different convergence rate than FC2, which is kind of what you were also talking about. And the alpha 2 occurs at different points at FC1 and FC2. So in a sense, you can think of that as, hey, each layer reached its optimal point at a different time step. And of course, on average, you can see that the place, I think that got kind of truncated over here, but on average, you see that the place where you have max test accuracy is approximately the place where alpha is near to. It's not exactly 2, but it's kind of near to. And you see this correlation trap and anti-Grokking phase, basically, where once it hits the 2 point, it goes all the way down to 1, which is a very, very heavy-tailed matrix.
I wonder if it would make sense to, so if you're proposing this as an explanatory mechanism for why the anti-Grokking takes place, I wonder if it would make sense to train to the point of sort of 10 to the 6th, and then split the experiment into maybe 3, or I'm not sure how many layers, maybe just 2 layers, and freeze one layer and freeze all the layers but one, and train the one, track just that one layer's changing alpha over time, and does that actually correlate to anti-Grokking on its own?
We actually do that in we have a large monograph, about 120 pages long, which describes the theory behind this, and we actually do that in the experimental section.
Awesome. Cool.
This is we don't look at Grokking specifically. What Hari's done is managed to reproduce this. He just basically did this all by himself, right? And it was able to show that the theory applies to this specific experiment as well. But we do exactly what you ask in a very related experiment.
Cool.
So yeah, basically to show that alpha less than 2 truly correlates with the dip in like test in general. So yeah, coming to the correlation trap, because now we might ask ourselves.
This is the mechanism.
Yeah. We see that you have this collapse, and we want to understand why is this collapse actually happening. So what we do is we take the layer matrix, the weight matrix for the layer, and then we randomize it. We basically do the shuffling. And if you think about it, when you shuffle this matrix, it should give you a Marchenko-Pasteur distribution with the ESD if your input distribution is not atypical. And what I mean over here is that when I randomize it and make it IID by Marchenko-Pasteur, it should follow this MP distribution for the ESD. The interesting thing is when you hit the anti-Grokking phase and you take the weight matrix and then you shuffle it up and then look at the ESD, you see these spikes that occur far, far away from the bulk of the MP distribution fit. So here is an example where this is like kind of right before collapse, where you see the single large eigenvalue. And then once you really get down to the collapse where you have like 40% or 50% test accuracy and alpha is far below 2, you see these spikes far away from the bulk. So this kind of tells you what exactly is going on. You have this very atypical ESD to begin with, and then you shuffle the weight matrix, and this essentially does not destroy these heavy correlations, which is why we call them correlation traps. So we fit it to an MP distribution, take a look at what falls outside. And these are basically really, really large eigenvalues over here and over here. And we take those eigenvalues and basically say that these large spikes are responsible for this anti-Grokking phase. So with respect to the experimental setup, I'm just reiterating it in case it was not clear. We took a 3-layer MLP. with ReLU on MNIST, and here what we did is our train set is vastly smaller than usual. Instead of taking like your typical 10,000, so on and so forth, number of examples, we took only 1,000 samples. So we have only 100 per class. We used Adam and the key condition, which is weight decay equal to 0, where the other progress measures had certain difficulties, is what we are really studying in depth. We do show later that the alpha equal to 2 and the alphas do correlate even in the case where the other progress measures work, which is the weight decay equal to 0.01, because you would want a negative control, right? So yeah.
Hari, we're a bit at time. Can we wrap up quickly, maybe so we have
Sure.
time for one
Yeah.
question?
Yeah. So here's just a visualization on the number of traps per phase. You have pre-grokking, you don't have any traps. You have grokking, you don't have any of these traps. You have anti-grokking, and you have several traps. Same thing with alpha. Big alpha with a large variance, a better alpha closer to 2 with a smaller variance, and then you hit a really, really small
Move the
alpha.
slide up.
Oh yeah, apologies. And then you have a really small alpha at the end. And that kind of encapsulates the big story, which is that you have this measure through HTSR theory that can differentiate pre-grokking and anti-grokking as separate phases. Something is very different between these phases, which is what we see with the correlation trap. And anyone interested, we can definitely discuss on the negative control experiments of weight decay 0.01, where you see that the alpha metric also plateaus with a plateau in test accuracy. And this is very important because you want to make sure that alpha just doesn't keep going below 2 and then test accuracy remains flat. That's not what you want to see, which is kind of what you see over here, which is that the average alpha remains flat. One layer actually flattens out above alpha equal to 2, and the other layer flattens out below alpha equal to 2. So kind of corroborating that each layer is learning something very different. And there's a lot with respect to that. But yeah, that is the whole story. Any questions?
Great, thanks so much for presenting, Hari. We're quite over time, and we're coming up to the end of the meeting, so I think we should wrap up here. Let's thank Hari for his presentation. I'm going to stop the recording. For anyone watching this, we have these research jams every couple of months. The next one is not scheduled yet, but it'll be soon. If you'd like to present, we welcome any submissions on the research jam website.